So far in our study of the properties of substances, we've been concentrating on substances where the phase is going to change. So where we have a liquid vapor mixture, or a superheated vapor. And we've been looking at how to use tables to find data when a substance is in that region. The next thing we want to look at is another class of substances called ideal gases. So we want to first of all talk about the ideal gas model. So ideal gas model is a way that we can represent the properties of these particular substances in a little bit simpler way than we had to for a substance that's changing phase. So the ideal gas model is made up of a couple of parts. The first one that might be familiar to you is the ideal gas equation, or the ideal gas law. So this relates the pressure, specific volume, the specific gas constant, and the temperature of an ideal gas. So the properties that are involved in this equation are P, V, and T. So you remember that the relationship between P, V, and T was really quite complicated when we were looking at the region where a substance was changing phase. However, for an ideal gas, there's quite a simple relationship between those three properties, and that's what the ideal gas law is. It's called an equation of state, and it relates these three properties directly in the ideal gas law. Now, the other part of the ideal gas model that is just as important as the ideal gas law is that the internal energy and the enthalpy become only functions of temperature. So this is a fairly significant simplification. You remember, in general, these properties, U and H, are functions of two properties. However, for an ideal gas, that's simplified quite a bit. So we want to start to get used to the fact that if we're dealing with an ideal gas and we know the temperature, that also tells us the internal energy and the enthalpy. So temperature becomes a very important property when we're dealing with ideal gases because it tells us the internal energy and the enthalpy. So both of these things, the ideal gas law and the fact that internal energy and enthalpy become only functions of temperature, are equally important aspects of the ideal gas model. Now, so far I've talked about ideal gases and substances that are changing phase as if they're two different things, but of course they're not. Really, the only thing that's different is the range of conditions that we're working with. So here is our PV diagram again. Here's our saturated liquid and saturated vapor lines, critical point at the top. We've talked lots about this diagram so far. We've looked at lines of constant temperature that go through that liquid vapor region, and there's an example of one of those. Here's a line of constant temperature that goes through the critical point, so that would be at the critical temperature. So we've talked a fair bit about those lines of constant temperature so far. Well, realize that we're talking about PV coordinates here, and that's two of the variables that are in the ideal gas law. So these are both lines of constant temperature. So the question is, what would a line of constant temperature look like for an ideal gas? Well, a line of constant temperature means that the entire right side of this equation is a constant. So that means for an ideal gas, on PV coordinates, a line of constant temperature is just an inverse relationship between P and V. So if we plot that, it's going to look like this. So as the volume goes up, the pressure goes down. As the volume decreases, the pressure goes up. So that is a plot of PV equals a constant. So notice all three of these things are isotherms. They're all lines of constant temperature. That one that goes through the liquid vapor region, this one that happens to go right through the critical point, and then this one that's at quite a bit higher temperature, and it's out in the ideal gas region where the shape of these lines can be modeled with the ideal gas law. So notice it's not a case of some substances being ideal gases and other substances not being ideal gases. It's more a case of where we are relative to this liquid vapor region. If we're in or near this liquid vapor region, we cannot treat these as ideal gases, whereas if we're out here in this region, we can, because the lines of constant temperature take on that shape. So here's just the same thing again, shown a little bit larger. So the key thing here is that PV equals RT, the ideal gas model, is not valid near or certainly in the liquid vapor region, because there's no way that that simple equation can describe these rather complicated lines of constant temperature. However, it does successfully describe lines of constant temperature if we get far enough away from this liquid vapor region. So that's really what we're talking about when we're applying the ideal gas model, is just a different region of the PV surface far enough away from this thing that the influence of it is not felt. Next, I want to discuss different forms that we'll see the ideal gas law take. So the one that I've introduced so far is this, PV equals RT. I want to point out a couple of things about this. Notice that the volume here I've written as a lowercase v. So that's the specific volume. That's the volume per unit mass. Because that's the specific volume, this is known as the specific gas constant. So PV equals RT is one form of the ideal gas law. Now, you may have seen this ideal gas law in several other forms, and we're going to review several of them right away here. So another way that you might see this is P capital V equals MRT. So PV equals MRT. Well, the gas constant here is still the same. That's still called the specific gas constant. Essentially, we've just taken this equation and multiplied both sides by the mass. So we see the mass showing up directly on the right-hand side. But the left-hand side, if we take specific volume and multiply by the mass, we get the so-called total volume, or meters cubed if we're working in SI units. So PV equals MRT is another form of the ideal gas law that we'll be using. And of course, they're equivalent. Another way that you might have seen this, or another way that we could write this, is on a molar basis. So notice both of these are on a mass basis. Remember, this specific gas constant is on a mass basis. If we were to look at the units of the specific gas constant in SI, it would be kilojoules per kilogram degree Kelvin, the kilogram being the important part of that for this discussion. So that's the gas constant, but on a per unit mass basis. That's why it's called the specific gas constant. So that word specific has the same meaning as it has when we talk about specific volume, per unit mass basis. However, this form of the equation is on a molar basis, and notice it's exactly the same as this one. It's just there's a bar over top of the V and a bar over top of the R. So now this volume is cubic meters per kilomole for in SI units, and therefore this is a gas constant on a molar basis. So its units in SI would be kilojoules per kilomole degree Kelvin instead of per kilogram. So this is also known as the universal gas constant. So R bar is the universal gas constant. And that's the one that you might remember from chemistry class. That's the 8.314 kilojoules per kilomole degree Kelvin. So the reason that it's called universal is that gas constant is the same no matter what gas we're looking at. So if we're applying this to nitrogen or oxygen or air or carbon dioxide, any ideal gas or any substance that we're treating as an ideal gas, then the universal gas constant is the same number. So when we work with this equation on a molar basis, it really doesn't matter which gas we're working with. Whereas when we work with it on a specific basis, which is actually much more common in this class, we need to make sure we have the gas constant here, the specific gas constant for the particular gas we're working with, because it'll be different for every gas. Next thing we want to look at is essentially the equivalent of this expression, but on a molar basis. So here we take this equation and we multiply by the number of moles on both sides. So this lowercase n here is the number of moles, so don't confuse that with a polytropic index. This is the number of moles in this context. So we have n r bar T here, number of moles, universal gas constant, temperature. And the left-hand side, we take the molar specific volume, multiply by the number of moles, and we get the volume. So PV equals nRT, where the R is the universal gas constant. So to convert back and forth between the universal gas constant and the specific gas constant, we do that with the molecular weight. So the universal gas constant divided by the molecular weight of the gas gives us the specific gas constant. So we can convert back and forth between those if we need to. The last thing that I want to point out or remind you of about all of the forms of this equation is that this temperature has to be in an absolute scale. So if we're working in SI units, that temperature has to be degrees Kelvin. If we're working in English engineering units, it has to be degrees Rankine. So you have to be careful about that. You cannot take degrees Celsius and put it in there, or degrees Fahrenheit. Ideal gas law will not work if you do that. Now the next thing we want to address is deviations from the ideal gas law. In other words, this is really a discussion of how can we tell whether we can treat a substance as an ideal gas or not? How can we tell whether we're far enough away from that liquid vapor region that we can use this more simplified version of the equation of state, just PV equals RT? And of course the fact that U and H are only functions of T. So when can we treat a substance as an ideal gas and when can we not? Well, the most common way to do that is using another property called the compressibility factor. So the compressibility factor, usually denoted by an uppercase Z, is defined as PV over RT. Well, if you take a look at that, you see that's related pretty closely to the ideal gas law. The ideal gas law is PV equals RT. So if we're talking about an ideal gas, or if we have an ideal gas, then Z is going to be equal to 1. So Z equals 1 for ideal gases. So the compressibility factor is essentially a measure of whether or not we have an ideal gas. So if the ratio PV equals RT is something different than 1, then we're not dealing with an ideal gas. We're starting to get too close to that liquid vapor region, and those lines of constant temperature are being distorted so that PV is no longer equal to RT. So this is a measure of whether or not we can treat a substance as an ideal gas. Now, like any other thermodynamic property, we can find Z if we know two other thermodynamic properties. So the two that we're going to use are temperature and pressure. Now, instead of using the actual temperature and pressure directly, what is typically done for compressibility factor is use something called the reduced temperature and the reduced pressure. And these two little equations here define what those are. So the P and the T in the numerator of these things is the actual pressure and temperature that we're at. So we've got a substance, it has a particular pressure and temperature, and we're interested in knowing is it an ideal gas or not. So the conditions we're at are defined by this P and T. The next thing we do is we look up the value of the critical pressure and the critical temperature for that substance. And we're going to do an example here in a moment where we see that. And that's this value in the denominator. We've talked about the critical point already. So this is the value of the critical pressure for whatever substance it is we're looking at, and the critical temperature. So those are the coordinates of the critical point, essentially. So the reduced temperature and reduced pressure is just the ratio of the actual temperature over the critical temperature, or the actual pressure over the critical pressure. So when we talk about reduced pressure and reduced temperature, they're essentially the temperature and pressure, but they're written as a ratio. So notice both of these would be dimensionless numbers. So when we take those ratios, we need to make sure that the units of T and TC are the same. This table shows typical values of the critical temperature and pressure for a few common substances. One of the ones we'll be working with a lot is water, so the critical pressure for that is 221 bar. Remember that 1 bar is about 1 atmosphere, so this is a very, very high pressure, and it's also a high temperature, 647 degrees Kelvin. Remember, 293 approximately is room temperature. Nitrogen and oxygen, on the other hand, still have relatively high critical pressures, 34 and 51 times atmospheric pressure approximately, but their critical temperature is really quite low, 126 and 154. Remember, that's degrees Kelvin, so those are quite cool temperatures. So whatever substance we happen to be dealing with, we can go to property tables and look up the critical pressure and the critical temperature. This is just an example of 3 of those. So the next thing we want to introduce here is a generalized compressibility chart. So a generalized compressibility chart is a graphical way to determine the compressibility factor Z from the reduced pressure and the reduced temperature. So a generalized compressibility chart is really telling us Z as a function of P and T. Now there's an extra step in there. We actually want to get the reduced pressure and the reduced temperature, but it's essentially Z as a function of P and T. So the way a generalized compressibility chart works, we're showing Z as a function of 2 variables. So we pick one of those 2 variables for the horizontal axis, and that's the reduced pressure, and Z is the vertical axis. So this just reminds us here of the definition of Z, PV over RT, and we're plotting that as a function of the reduced pressure. Well, first thing to realize is there is an important value of Z here that we want to show on here, and that is, of course, Z equals 1. If we're somewhere along that dotted line, then we have an ideal gas because Z is equal to 1 on that dotted line. Now, because we chose pressure for this horizontal axis, we're going to draw lines on here which represent lines of constant reduced temperature. And there's going to be a whole family of curves on here, each of them at a different value of the reduced temperature. So I'm not plotting this accurately. This is just a sketch. We'll see an accurate generalized compressibility chart on the next slide. But as an example, if we have a reduced temperature quite a bit greater than 1, it would look like that. Notice a very, very high reduced temperature would mean we're a long ways away from the liquid vapor region, and it would lie right on top of this dotted line. But as we reduce our temperature from that very high value down closer and closer to the critical temperature, what started off as perfectly flat lines will start to deviate, and this deviation away from that horizontal dotted line starts to show us deviations away from the ideal gas behavior. And as we bring that temperature lower and lower, that curve is going to be deflected more and more until we finally get to the last one that we typically show on here, and that is a reduced temperature of 1. So notice this is the line of constant temperature that's actually going right through the critical point. So this is really just an alternate way to show the distortion of those lines of constant temperature away from ideal gas behavior as we get closer and closer and closer to the liquid vapor region. So many different gases lie on the same lines when we plot them in this way. In fact, that's the reason that this is called a generalized compressibility chart, is because we can use it for lots of different gases. And in fact, the reason we can do that is because we're using reduced pressure and reduced temperature, so that a single chart can be applicable to a variety of gases when we use reduced pressure and reduced temperature. Now, you can certainly get compressibility charts that are made for specific gases. You can get compressibility charts for oxygen. You can get compressibility charts for nitrogen or other types of gases. For those, this would just be pressure and this would just be temperature, but you can only use it for that gas. The other thing to remember is that the whole purpose of this compressibility chart is to check whether a gas can be considered ideal or not. So can you use the ideal gas model, or should you go find more detailed property tables to get the properties for that gas? Next, we're going to illustrate how this works with a short example. Let's say we have nitrogen at 100 kPa and 300 Kelvin. So just a couple of things about those conditions before we actually look at the numbers. First of all, nitrogen, of course, is the most common component of air. So to a first approximation, we're talking about air here. Air, of course, is actually a mixture of nitrogen and oxygen and a few trace elements, but to a first approximation, this is air. Not only that, but 100 kPa is very close to normal atmospheric pressure, and 300 Kelvin is very close to room temperature. It would be a little bit warm, 27 degrees C about, but the point is that these conditions here are not all that far away from just air at standard conditions. Now, we probably know that we typically treat air as an ideal gas, and so we'll see if this compressibility factor confirms whether we should be doing that or not. We could do this example with lots of different properties here and see how it works out, but this is one where the conditions sort of tell us ahead of time we should expect this to come out with a compressibility factor fairly near 1, because we usually treat air as an ideal gas at these conditions. So let's see how this works. Well, first thing that we would do is go and find the critical pressure and temperature for nitrogen. And table A1 in your textbook has that, and we had that in a little table in our lecture notes here a moment ago. The critical pressure is 33.9 bar, and here I've just converted that to kPa, and the critical temperature is 126 degrees Kelvin. So that's nitrogen. And the critical temperature is 126 Kelvin. So we need the critical pressure and temperature because we need to calculate the reduced pressure and temperature. So notice, to get a reduced pressure, you take your actual pressure and divide it by the critical pressure. And so this is why I converted this critical pressure to kPa, to get it in the same units as the actual pressure so that we can calculate that ratio. So the reduced pressure is 0.029. Likewise, the reduced temperature, calculated in the same way, actual temperature divided by critical temperature, is 2.38. So we now have these two values of reduced pressure and reduced temperature, and we want to take those to a generalized compressibility chart and see what the compressibility factor is. So here's a generalized compressibility chart out of your textbook. So this is figure A1 out of your textbook. And of course this looks a lot more complicated than the little one that I sketched earlier on, but that's because it's, first of all, it's drawn accurately. It's drawn to scale, so we can actually pull numbers off here, and it has a lot more lines of reduced temperature on it. So just to orient ourselves to this, first of all, realize the vertical axis is the compressibility factor, and they show its definition here as well, PV over RT, and the horizontal axis is reduced pressure. Now this particular compressibility chart only goes from a reduced pressure of 0 to 1. Typically these compressibility charts are drawn on several pages, and each page covers a different range of reduced pressure, just so that you can zoom in on that range and give a little more accurate chart for reading numbers off. So the axes are as we would expect. Now each of these solid lines here has a label on it for the reduced temperature. So notice this line right at the top that is essentially a horizontal line at a value of Z equal 1 is labeled reduced temperature of 5. So that means for a reduced temperature of 5 or above, nitrogen behaves as an ideal gas. But as the reduced temperature decreases, so notice the next line is 3, next line is 2, 1.6, 1.4, down, down, down. As the temperature decreases, we get closer and closer to that liquid vapor region, and the distortion, or how far this line is away from Z equals 1, becomes greater and greater and greater. So let's use this to look at our conditions. Now I've forgotten what they are, so let's just go back here. So we need a reduced temperature of 2.4, we'll say, and a reduced pressure of 0.03. So that's what we're looking for. So first of all, reduced temperature of 2.4. Well, that's partway between 2 and 3. So partway between 2 and 3 is the line that we're interested in. Now there isn't a line there, of course, we just have to sort of interpolate between those two. But we can tell right away that even up to a reduced pressure of 1, we're going to be very close to an ideal gas, because both 2 and 3 are quite close to a Z value of 1. Now not only that, but the actual value of reduced pressure that we're looking at, remember what it is? 0.03, we'll call that. Well, that's 0.1. This would be 0.05. So 0.03 is about here. So not only are we at quite a high reduced temperature, but we're at a very, very low pressure. Very, very low reduced pressure. So our point is there, and essentially Z equals 1 is the conclusion we would come to. So this generalized compressibility chart has confirmed that nitrogen at 100 kPa and 300 Kelvin is an ideal gas. It behaves as an ideal gas. But if we were to look at different conditions, like let's say we reduce the temperature of that nitrogen way down so that its reduced temperature was 1.2, and we looked at higher pressure applications where maybe the reduced pressure was 0.8. So in those conditions, our compressibility is definitely not 1, and we would not be able to treat nitrogen as an ideal gas under those conditions.